Uh, at the beginning, I describe what the script does: amplitude, AM, FM, and PM, modulation and demodulation in one file. First, AM part, AM double sideband with a carrier, double side banded suppressed carrier. SSB using helper transform envelope detector for AM, Cohen-Hard detector for AM and double sideband. FM part narrow band, FM wide band, FM with direct integration method, FMD demodulator using differential and envelope. FM demodulate using zero crossing rate, FM BM part narrow band, BM wide band BM with the direct phase modulation, BM demodulator using differential and arctangle. It is written that it works both in MATLAB and Octave. This command just and second, clearing the workspace. Clear CLC close all, clear removes all variables from memory. CL clears the command window, close all, close open figure windows. This ensures that script started from clean state every time. If existing Octave version built on equals 0 BKG load signal int. This if blocks checks if we are running in Octave, not MATLAB. In Octave, many signal processing function like helper butter are in the signal package, so we load using BKJ load signal. In MATLAB, this block is skipped because MATLAB already has those function. Common common parameters time message carrier fs equal 2000 sampling frequency t times equal 1 fc sampling period t equal 1 total simulation time second t equal 0 ts time vector uh, t equal 1 total duration the simulation is 1 second t equal 0 ts the time vector from 0 to 1 second with step ts fm equal 5 message frequency 5 hertz am 1 amplitude of the message is 1 fc equal 100 carrier frequency 100 hertz ac equal 1 carrier amplitude fc equal 100 carrier frequency is 100 hertz ac equal 1 carrier amplitude is 1 am cosine 2 by fmt message cosine. Here we define the message signal mt as a cosine with the frequency fm and amplitude am. Am family am double sideband with the carrier mu equal 0.5 modulation index equal or bigger than 1 carrier equal cosine 2 by fct carrier. Sam ac equal 1 plus mum carrier am double sideband with the carrier mu equals 0.5 modulation index of the am signal less than or equal to 1 carrier cosine 2 by fct carrier signal with a frequency fc. Sam equal ac plus 1 mu carrier standard am signal. The term 1 um is modulating term, then is the amplitude multiplied with the carrier. ENVAM ABS helper AM helpers compute the analog signal of the AM waveform. ABS gives the envelope of the AM signal figure. Plot TSAM hold on. Plot TENVAM R line widths 2. Plot ENVAM R line widths 2. Grade on. Title AM double sideband with a carrier and envelope XLA label time. Y label amplitude legend. AM signal envelope X lime 0 0 0.4. This figure shows AM signal. It is positive envelope, negative zoom in the first eurosecond from the clarity. 5.2. 5.2 envelope detector AM demodulation MEMV-DT. AM is ideally AC. MUMT to recover MTU, subtract the DC term AC, then divided by AC MU. MEMV-DT is recovered message using envelope detection. Figure plot TMK, TM, are grade on title envelope detector from AM recover versus original. X label time, S, Y label amplitude, legend original message recovered. This figure composed the original message MT with the recovered message from the envelope detector. 5.3 D double sideband suppressed carrier. The double sideband AC double sideband is simply the product of the message and the carrier. No DC term. Double sideband suppressed carrier ACMT cosine 2 by M 2 by FCT figure subplot 2 plus 2 1 1 plot TM grade on title message MT. X label time S, Y label amplitude X line 0.4 subplot 2 1 2 plot 2 2 1 2 plot double sideband suppress carrier grade on title double sideband suppress carrier signal X label time S, Y label amplitude X line 0.4 first subplot message signal, second subplot double sideband suppress carrier signal. 5.4 suppress using Hilbert transform. M analyzing Hilbert analyzing representation of the message MH IMG. M analytic Hilbert transform 90 degrees phase shift. M analyzing the complex analytic signal of MH equal MH. M analyzing is a Hilbert transform of M which is 90 degrees shifted version. Sideband suppress carrier USB EC. M equal cosine 2 by FCT MH sine 2 by FCT percent upper sideband SSB LSB ACM cosine 2 by FCT MH. These two formulas generate SSB USB upper sideband SSB signal SSB LCB lower sideband signal. They combine the original message and it is Hilbert transform with the cosine Hilbert transform with the cosine and sine figure subplot 311 plot TM grade on title message MT subplot 312 plot SSB USB title SSB upper sideband USB subplot 313 plot TS SSB LCB title SSB lower sideband LSB. This figure shows the message USB signal and LCB signal. 5 Cohen hard detector for AM double sideband SC and SSB. Local carrier is an ideal local selector with the same frequency and phase as transmitted carrier. FCUT 5100 15% Hz BA butter for FCUT FS divided by 2 equal the fourth order Butterworth LBF. Here we design low pass filter. Cut-off frequency is 15 Hz, slightly above the message frequency 5 Hz. But therefore design fourth order butter low pass filter and add the filter coefficient. Cohort detection for standard AM Y mix AMS AM2 local carrier MCOTHM raw fillet BAY mix AM MCOTHM equal MCHAM raw AC. Multiply this receive AM signal by 2 cosine 2 by FTCT. This shift is a spectrum down to baseband filter is applied low pass filter with zero phase delay. The raw output still contain a DC term, so subtract AC and divided by ACMU to obtain recovered message. Cohort detection for DSPC CY mix DSPC well S 2 multiply with local carrier. Similar process multiply with the carrier and low pass filter for DC. The result is approximately ACMT. So you divide it by AC. Figure plot 2MKH. Legend original from AM from the figure. Compare original message recovered from AM recovered from double sideband suppressed carrier. Cohort detection for USSB figure shows the estimate instantaneous frequency. The raw message estimate the filtered estimate compared to the original. Last PM family narrowband and wideband PM. Phase division constant, small value narrowband, large value wideband. Phase modulation signal instantaneous to Y with the direct phase and modulation figure. Plot the PM signal demodulation differential and arctank. Differentiate the phase division with respect to time. This derivative proportional to derivative removes the low pass filter to get smooth output. The result is proportional to dMdt, the time derivative, the message. First subplot PM signal. Second derivative of the phase. Third demodulate output related to the derivative of the message. The end of the script.